our series. Kind greetings to you all. We continue with our series on carbonyl compounds. Hope my screen is visible. We had explored reaction with hydrogen cyanide. This is the reaction with the sodium hydrogen sulfide. How do carbonyl compounds react with sodium hydrogen sulfide? Carbonyl compounds react with saturated solution of sodium hydrogen sulfide at room temperature to form white precipitates. Now, this reaction is also essential. This reaction can as well be used to confirm the presence of carbonyl functional group within aliphatic carbonyl compounds. So meaning that when aliphatic carbonyl compounds are treated with saturated solution of sodium hydrogen sulfide, the observation is white precipitate. I take note of that. Saturated sodium hydrogen sulfide solution can also be used to confirm for the presence of carbonyl functional group within aliphatic carbonyl compounds. Below is the reaction mechanism. I take an example of ethanol with sodium hydrogen sulfide. So the mechanism occurs as follows. Sodium hydrogen sulfide in solution is made up of two ions. In solution, it is made up of two parts. Sodium ions and hydrogen sulfide. Those are the two parts which make up sodium hydrogen sulfide. Then I bring my carbonyl compound. I expose the functional group very well. Like that. Then from bonding, they taught you that the hydrogen sulfide anion has this structure from bonding. And there are only pairs of electrons on sulfur. They are there. So this bond is polar. Oxygen takes, then carbon becomes electron deficient. The only pairs of electrons that are present on the sulfur atom are donated to carbon, because carbon now is electron deficient. Why? Oxygen has taken away electrons from it. That. Therefore, what do we form? We form CH3. See, this is now a single bond with oxygen, which has a negative. This carbon carries the hydrogen, and I am bonding that carbon with, that carbon is bonding with S. That S, look at that S very well. It carries 3 oxygen atoms and H. like that. Now, what have I left out? There's one thing which I've left out here. Once this sulfur donates to carbon, once that sulfur donates to carbon, that sulfur will be having a plus. However, that plus is neutralized. Why? Once sulfur donates, then it becomes electron deficient. Here we have excess electrons. So we donate to sulfur like that. That's why sulfur is not having a plus. I repeat, once sulfur donates, as in, okay, we start with oxygen taking. Carbon becomes electron deficient. There are lone pairs of electrons on sulfur. They are donated to carbon, which is electron deficient. Sulfur becomes electron deficient. Here we have oxygen with a negative charge, so it donates electrons to sulfur. What have I said? I repeat, within this carbonyl compound, the carbon to oxygen double bond is polar. Oxygen takes, carbon becomes electron deficient. It needs electrons. Within sulfur, we have lone pairs of electrons on sulfur. They are donated to carbon. Now, once sulfur donates to carbon, sulfur becomes electron deficient. But this oxygen has excess electrons due to this negative charge. So we donate to sulfur. Is it clear? I repeat for the last time. Within the carbonyl compound, the carbon to oxygen double bond is polar. So oxygen takes, carbon becomes electron deficient. It needs electrons. Within this compound, sulfur has lone pairs of electrons. They are donated to carbon. Once we donate to carbon, sulfur is not now having those lone pairs of electrons. It becomes electron deficient. Here we have oxygen with a negative, so it is electron rich. It donates to sulfur. Therefore, this sulfur is not having a plus. Now, sulfur is not having a plus, but this sulfur can lose the hydrogen here. Are you seeing this group? This group in solution, it ionizes to form, it splits so that we form a radical which is negatively charged, the SO3. It forms the SO3 with a negative and the H with a plus. Yeah. Am I saying this oxygen, the oxygen hydrogen bond within SO3 is polar. Is polar because oxygen can take electrons, so that we have SO3 with a negative and hydrogen with a plus. So what do we have there? So in this case, we are going to have a hydrogen shift. We are going to have a hydrogen shift. Have hydrogen shift. Which hydrogen is shifting? That hydrogen which is attached to SO3. So it shifts so that it goes where we have electrons up there. So we shall have CH3, C, OH, H, SO3 with a negative of that. Now the sodium ion is added to this so that we form a white precipitate. So that is the white precipitate, which is CH3, C, OH, H, and what's its name? Its name is coming from, it is coming from ethanol. So this is ethanol sodium hydrogen sulphite. The name is ethanol sodium hydrogen sulphite. I take another example. Propanone. Propanone reacting with sodium hydrogen sulphite. So what do we form? Before we look at what we form, we first deal with sodium hydrogen sulfite. It breaks down to provide sodium ion and hydrogen sulfite ion. Let me hope I started with this. Yeah. Then I expose my functional group properly. The carbon to oxygen double bond. It is polar, so oxygen takes. Carbon becomes electron deficient. Then I bring my hydrogen sulfide. From burning hydrogen sulfide, iron has this structure. There are lone pairs of electrons on sulfur that are donated to carbon. Now, once sulfur donates, it also becomes electron deficient. Here we have excess electrons that are donated to sulfur. So what do we form? We form CH3. C, this is a single bond, O has a negative. It carries CH3. I am bonding it with S, which carries 3 oxygens and 1 hydrogen. Note that this group, within this group, we have the oxygen hydrogen bond. We have the oxygen hydrogen bond, which is polar. So we can have oxygen taking so that this part here, so that this thing splits into SO3 with a negative and H with a plus. In simple terms, this hydrogen shifts where we have electrons. So at this level, have hydrogen shift. Hydrogen shift resulting in formation of CH3, C, OH, CH3, SO3 with a negative like that. Then here, sodium is added so that we form a white precipitate. So we get CH3, OH, CH3, SO3, Na, like that. So we have CH3, OH, CH3, it is coming from what? Propanol. What is the name? Propanol, sodium, hydrogen, sulphite, white precipitate. Another example. Which example? I think those ones are enough. Let me finalize with CH3, CH2, CHO with the saturated solution of sodium hydrogen sulfite. So the solution is saturated, implying that it has too much of sodium ions and hydrogen sulfite. So the salt splits so that we get a sodium ion and a hydrogen sulfide ion, like that. So I continue. I expose my functional group properly. CH3, CH2, carbon to carbon, carbon to oxygen double bond, like that. Chemistry does not change. The chemistry does not change. This is a polar bond because oxygen is more electronegative than carbon. So it takes carbon, it becomes electron deficient. So I bring my hydrogen sulfide ion. I properly from bonding. It has this structure. There are lone pairs of electrons on sulfur, which are donated to carbon. Once they are donated to carbon, sulfur becomes electron deficient. I give it electrons. Once I give sulfur electrons, this is what I'm forming: CH3, CH2, C. This is now a single bond, O, with a negative. This C carries H. I am bonding it with the S, which carries 3 oxygens and hydrogen, like that. From the previous examples, we have said that this splits. So that hydrogen goes to where we have electrons. So where I have excess electrons. So at this level, we have a hydrogen shift. A hydrogen shift resulting in formation of CH3, CH2, C, OH, H, SO3 with a negative, like that. Then at this level, I add sodium. On addition of sodium ions, since the solution is saturated, they are present in excess. They are added to that so that we get our final product. I have named a lot of compounds, so I don't need to name that. Maybe to just complete my equation here. Will this space be enough? I think it is more than enough. This is C. Carries any OH. Like that. Kindly try out these questions. I have worked out the examples. I believe they are enough. Aldehydes, I have used ethanol. I started with ethanol. Then I have also used the propanol and the propanol. I don't know. I believe those examples are enough. Enough to make you understand. Kindly try out these questions. Okay, let me go. I don't know. My heart is telling me that the examples are not enough. Okay. Let me finalize with this one. Cyclohexanone with the sodium hydrogen sulfide. How does it behave? It breaks down. It breaks down so that we form sodium ion and the hydrogen sulfide, like that. Then I bring my carbonyl compound, cyclohexanone, expose the functional group. We are lucky that here the functional group is exposed very well. So the carbon to oxygen double bond is polar. Oxygen takes, carbon becomes electron deficient. Then I bring my hydrogen sulfite ion, and from bonding it has this structure. There are lone pairs of electrons on sulfur. So they are donated to that carbon. Therefore, what do we get in this case? This is now a single bond. Oxygen has a negative. I am bonding this carbon with S, which carries 3 oxygens and a hydrogen. Here we have a polar bond. We have a polar bond between oxygen and hydrogen. So meaning that oxygen can take so that hydrogen is lost. Therefore, in this case, hydrogen looks for where we have electrons. So we have a proton shift. OH. Like that. Then sodium is added. So that we get our desired product. So what is the product here? It's the product. I leave some simple questions for you to try out. Those examples are more than enough. More than enough. I need to try out the following. Butanol, cyclohexanol, with the sodium hydrogen sulfide, and also here with the sodium hydrogen sulfide. You see how we are moving? We are moving at a moderate speed. What have we so far covered? What have we so far covered? All these things have been taught. Condensation reactions. We have covered nucleophilic addition reactions. They have been covered. Condensation, they have been covered. Now, where am I moving next? Redox reactions. Redox reactions of carbonyl compounds. And under that, we are going to see that there are those that are reduction. There are those that are redox. I think I'll start with the reduction. Yeah. The other stream, I think I started with the reduction. So let me maintain that order. So this is another reaction. These are other reactions. Carbonyl compounds. Reaction 3. Reduction. I think this is part C. Reduction and oxidation reactions of carbonyl compounds. Reduction and oxidation reactions of carbonyl compounds, like that. So under this, we start with Roman 1, reduction reactions of carbonyl compounds. Let me see. I think I still have time.